Okay. Welcome, everyone. I'm Shpresa Halimi, Research Assistant Professor. Carol, can you talk to her? Okay. Let's do this one more time. Welcome, everyone, to the third in our weekly seminar series. I'm Shpresa Halimi, Research Assistant Professor with the Institute for Sustainable Solutions that is sponsoring this seminar series. I would also like to welcome our online audience. They are watching us through the Solutions Journal website, and we are encouraging them to ask questions at the end. During our Q&A sessions, we will have an opportunity to address their questions. Before I introduce tonight's speaker, I have a couple of announcements. And for those of you who have been coming every week, they probably are familiar, but for those of you who are kind of new, I just wanted to let you know that we do have a half an hour for questions and answers. So please feel free to ask questions, and please come up at the mic that is in the middle aisle. We also can continue our discussion over some refreshment. So there will be a small reception after the talk. Those students who are taking the class for credits, please come and see me and Carol after the lecture so that we can hand out the papers and give you some feedback on the weekly reviews. The theme for tonight's lecture, or the title, is Collaborative Solutions for the Mighty Columbia. And tonight's speaker is Professor Heejun Chang. Heejun Chang is a professor of geography here at Portland State University and a fellow with the Institute for Sustainable Solutions. His interest in climate change and water actually started since he was a little kid, and in his backyard stream, located in the foothills of Bukhan Mountains in northeast Seoul, Korea, where he once decided to construct or to build a dam to divert stream water to a pond, and then that allowed him to observe the fluctuation in water levels throughout the year. Professor Chang's research areas include impacts of climate variability and change on regional water supply and demand, land cover change and water quality, integrated water resource management, and urban flooding in monsoon Asia and the Pacific Northwest. He has inspired transdisciplinary water research at PSU and beyond, as demonstrated by his collaboration with multidisciplinary and international scientists and various water stakeholders in examining complex water issues at multiple scales. Professor Chang recently served as a lead author of the freshwater section of the first Oregon Climate Assessment Report. He is currently a representative of the Willamette River Basin in UNESCO's HELP, Hydrology, Environment, Land, and Policy Program. Professor Chang holds a PhD in geography from the Pennsylvania State University. Please join me in welcoming Professor Chang.
Thanks for the introduction. I'm really glad that everyone be able to attend this session. And I'm not a mighty person to actually solve all these solutions, but I'm trying to give some possible ways how we can solve complex water problems in the Columbia River Basin. Just to give you a background of this research, this is part of sponsored by Institute for Sustainable Solutions. We had a summer collaborative research back in past summer, and it's still ongoing. And I'd like to also acknowledge multiple co-investigators, including folks from environmental science and management, like Arlen Yekli and Yangdong Pan and Mark Zisma, and also my colleague Martina Franz and Il-won Jung. He's back there sitting and watching my talk. And Vivek Shandas from Urban Studies and Planning. And also we have two engineers, Dave J. and Hamid Morkani. So as you see, this is really interdisciplinary and transdisciplinary research. We are trying to solve and what are possible ways to understand these complex water problems. And also we do have 5 GRAs who had worked on this project. So when you talk about the water resource prediction, there are a lot of uncertainties associated with that. So if you look at the observed data, so we assume that this is based on, let's say, data from 1900 to 2000. We only have 100 years of record. But water resource manager need more data than that. So we need to look at further back, like what happened in 16th century, or what's going to happen in the 21st century. So without understanding of those, what happened in the past and what might happen in the future, so our water resource management may not be sustainable. So what kind of information do you need to predict the future scenarios? First, so we need to gather those information. What information is available right now? And once you understand that information, we also can imply what might happen. And then once we understand what might happen in the future based on analysis, we can find a way to do something, so we can do some actions in terms of adaptive water resource management. And you can see there are a lot of factors that we need to consider in terms of predicting our future water resources. So the climate change is one of the many driving forces. We have witnessed that global temperature has risen substantially in the past decade, the past century or so. But also there's an interannual or decadal climate variability that also should be considered in analyzing any water resource aspects. But also humans modify landscape. So land cover change, we all know that urban development can increase storm runoff, but also increase water demand. So we need to understand those dynamics. So as part of this collaborative research, we have identified some research objectives. So fundamentally, we are interested in looking at the whole Columbia River Basin and identify what are some vulnerable areas within the basin under the stress of climate change and land use change. And we realized that Columbia River Basin is really complex, and as a result, we singled out 3 representative basins, which I show you later. So some expected results of this research include, so we understand what are the impacts of human activities on water resources, including anthropogenic climate change and urban development and upstream deforestation. And also, once you understand those human impacts, we can also develop some potential adaptive strategy. And to be able to develop these adaptive strategies, we also need to identify what are current knowledge gaps. So what kind of data are available right now, and what additional data we need to be collected and why. So here are some multiple choice questions, maybe the water resource 101. So anyone has an idea of which county in Oregon use water most? The Multnomah has 3 counties in the Portland Metro, and also Deschutes County. Deschutes? Okay, the Deschutes County, raise your hand. So how many? Okay, almost half of them. Any other answers? Yes? Clackamas? Yes, both are right. So it could be either Clackamas, depending on how you look at the problem. If you look at the total amount per day, that's Clackamas. But if you look at per person, the Deschutes River Basin actually is number 1. So not surprisingly, the Clackamas and those 3 counties have more people living in there. So in other words, the implication of this is even in the state of Oregon, we have very different situation in terms of water demand. So we have to understand those spatial variability. Another question. So how much do we need for irrigation? Number 3, close. Number 2. So it's 5,700 mega gallons per day. That's based on the annual average. Yeah. But not surprising, irrigation only occurs during mostly summertime, so you cannot consider this is, yeah. So it might be actually more than this if you actually focus on the summer months. And another question, looking at the water quality. What is the most significant water quality problem? Is it water temperature or nutrients, sediment, or E. coli? Number 2? Number 1? Number 2? Okay, looks like number 3. The answer is number 1. The water temperature is the most significant problem. So we have listed temperature impaired streams, which I'll show you later. And it's a little bit more complex now. So now here are 3 locations in Oregon. So one in coastal region and the other in the Willamette, close to Mount Hood and where Sandy River is. And third, the Umatilla River Basin in northeastern Oregon. So what you see here is the very different shape of hydrograph. So this is called hydrograph. You can see the changes in runoff over time, so from October to September. So October is the beginning of the water year, so that's why we start from October, not from January. So the December we have the highest peak flow in Wilson River, so we get more precipitation. So this is pretty much rain-fed, rain-dominated system. But if you look at Blazed Alder Creek, which is in Sandy River, you have 2 different peaks. Anyone know why we have 2 different peaks here? So one responds to the winter precipitation, and the second peak responds to snow melt. So you can see the snow melt is very important part of water supply in subsequent months. And Umatilla Basin is pretty much driven by the snowfall. So the peak flow won't occur until April. So the question is, if climate is changing, so what kind of changes would you expect? So in the rain-dominated system, so a lot of climate projection models predict that we're going to have more rains in winter. As a result, the peak flow will increase, but the timing doesn't shift at all. In rain and snow, this is called a transient basin. So we only now see one peak. So because snow is gone, so there is no second peak anymore. So that means, and also we have a reduced supply in subsequent summer months as a result. In the snow-dominated system, there's also changes in the peak timing from late spring to early spring, and also subsequent decline in summer flow. So that means a water resource manager should prepare for these potential changes in the system. So many of you may have seen this picture. This is taken from the IPCC report, the Intergovernmental Panel on Climate Change. So I just zoom in the Pacific Northwest and looking at changes in temperature and changes in precipitation. So, and also looking at by annual scale and also by season, so winter and summer. So what's interesting here is just looking at annual scale, we have about 3 degrees Celsius of warming by the end of 21st century. So this is based on like 9 different global climate models called ensemble mean. So take the average of these different models, because each model has a very different assumptions and they project slightly different way. But if you look at the winter months, they have more, actually slightly less warming than the annual average. But the summertime may get like a 4 degrees Celsius of warming. So that means you get water may evaporate more during the summer when we need water most. If you look at the precipitation, there's quite uncertain. And if you look at this, there's almost no changes in annual precipitation. But if you look at by season, so the winter months, this corresponds to this about 20% increase in winter precipitation. In summer, up to 20% decrease in summer precipitation. So if you combine those changes in precipitation and temperature in summer, you may expect that we're going to have more significant water stress in the future if those model predictions are right. But also population growth is another main driving forces of landscape change. So this is showing decadal trends in population and also some projections in the Columbia River Basin, broken down by each state. And this is just showing increase in the spatial extent of growth areas since early 20th century. And this is showing where most people live in the Willamette and also the rest of other Columbia River basins by county level. But another dimension we also need to consider is the humans actually manipulate the whole system. So we create dams, try to store water and then release water later for a number of different reasons, including flood control and release water during low flow season to augment flow. And we also created fish ladders, try to get fish migrate upstream. But this is just showing all the dots represent the number of dams in the Pacific Northwest. Imagine how many dams are in our region. But also people try to protect some bank stabilization and by planting those trees. So when you talk about the water resource management, so we have to understand those three different angles: the climate variability and change, and land use, land cover change, and water resource management, how the society responds to those changes. And then we have also understand different aspects of water resources, including water supply and water quality, and some extreme events like flood and droughts, and water demand. And increasingly, also, we have the water-related ecosystem services. How many of you heard about the concept of ecosystem services? So what is it? What is ecosystem service? It's monetary value of nature. Okay. So what kind of benefits we get from the nature? So the environment economists come up with some valuing system, and including like a water supply, for drinking water, or like a temperature regulation, so it can help sustain a fish. But also the scale is important. So everything is occurring at very different scales, and different factors explain those differences. So traditionally, in water resource science community, there are two separate communities. One is more scientific community, and the second is water resource managers and stakeholders. Those two communities, they didn't talk with each other. As a result, there's a called paradigm lock. So most hydrologists start from some research questions or hypotheses, rather than talking to stakeholders. And they don't necessarily understand what are some problems that stakeholders would like to solve. Vice versa, the stakeholders don't consult scientists. So they always have their own way of looking at the problems and try to solve those. So we need to break those paradigm lock. So how do you do that? So this is part of my involvement in the UNESCO HELP program. So this is called for HELP stands for Hydrology for Environment, Life, and Policy. So as you see, the mission of this program is try to deliver both social and economic environmental benefits, and how we engage those stakeholders at the beginning of the project, and how the science, hydraulic science can be helpful to solve those problems. So not only deliver useful information, but also some usable information to those stakeholders. That's the kind of fundamental change in philosophy in these days. So this is the way most scientists do. So scientists come up with some data collect, and then you analyze it, and then you develop some model, or you develop scenarios, and then deliver that to the stakeholders, and then you say that the decision support system. So what's missing here is you don't consult the stakeholders at the beginning, so we have to break this vicious cycle.
So one way we can do this, we move the stage 5 at the beginning. So this is a new cycle. So we have to consult the stakeholder at the beginning and participate then. So now the stakeholders take some ownership, and then they can give some honest advice to the scientific community. And the scientists also understand those issues, what stakeholders like to solve, and then we can identify some action plan, and then you can do some more end-to-end research together. And this shows the Columbia River Basin, and there are a lot of, this is actually one of the biggest river basins in the United States, and also it's an international river basin, so actually the headwater is in Canada. And as you know, this is taking the majority of land in the Pacific Northwest, about 8 million people living in there. And we analyze everything by county level because the county has the most socioeconomic information, and also the water use data are organized by county level. So this is a kind of unit of analysis. So I'm going to talk about some issues one by one, starting from the water supply first. So this is based on the USGS water consumption data. So they actually publish data every 5 years. So we take the data from mid-1980s and up to 2005 and try to identify which county within the Columbia River Basin, so the U.S. portion of the Columbia River Basin, uses most water, and if there's any change in those spatial patterns, and you try to explain why some counties use more water than other counties, and how they are related to any changes in land cover or population growth. So you can see there are apparently some hotspots in the state of Idaho, and does anyone speculate why those states use more water than the rest of other parts of the Columbia River Basin? What activities are in those counties? Agriculture, irrigation. And then, but also we know that those areas are pretty dry compared to wet western Cascade here in the Willamette. So where do they get water then? In addition to water from streams. They also mine groundwater, right? So this is showing the groundwater usage over time. And do you know what county is this? This county in Oregon? A lot of the big Indian reservation here, Umatilla County. So what happened in this county in the past more than 40 years, there's a steady decline in groundwater level since mid-1960s. So, but we all know that this county produces a lot of crops, and agriculture is the main source of economy in this county. So where do we get additional water in the future if this trend is going to continue? It is not sustainable. Is there any solution to solve this problem? Anyone read the news in a couple of weeks before in Oregonian? They're trying to take water from the main Columbia River and take the water during wet season and store that in the ground. And this is called aquifer storage recovery. And there was a feasibility study a couple of years ago. And they take surface, this is from the Columbia River, and then treat it, and then store that in the wells and pump that up during summer times when people need more irrigation water. So this is one possible solution, how those dry areas can augment their water resources. And also we are interested in looking at how much water is available, how much water they can get from nature. And we look at the water availability. This is based on some simulation modeling of the climate impacts group at the University of Washington. So the water availability is generally low in the drier portion of those counties. And then we also look at whether there's been any change in water availability in the past decade or 2 decades. So if you look at this bottom right corner map, you see significant decline in water availability. So the precipitation has been constantly declining in the past 20 years. So the majority of all parts of the Columbia River, you see about up to 20% reduction in water availability. And then we come up with some simple index. How vulnerable are those regions, counties in our case? So the water resource vulnerability is defined as how much water each county uses and divided by how much water is available. It's a simple index. So what that means is the vulnerability is going to increase 2 different ways. Either you increase water use or decrease water availability. So not surprisingly, those counties in Snake River and the Spokane and the Yakima Valley, they are more vulnerable than the rest of other parts in the Columbia River Basin. And then we also try to look at how much water is used by each sector. So the type of water needed in each county. So as you see, those counties in the Snake River, the irrigation water is the major consumption. But in the Willamette River Basin, we have also other water usages. And also we compare that, the water resource vulnerability to land cover conditions. And the higher the vulnerability, as you see, it tends to have more ag land. So the land cover is another factor that explains those variability in water vulnerability here. So that means that when climate is shifting, so we need to understand how there is a complex interaction between the climate and also land use and water consumption. So those 3 angles should be tied together to help understand the system dynamics. So if climate change, how much water would you expect? This is one of the modeling case study in the Willamette River Basin, and Heejun Chang is also a co-author of this paper. And we look at changes in seasonal flow. Remember that a lot of these climate change scenarios, they project a different changes by different seasons. So we look at this by winter and summer. And on the for 2 different time periods, one in the mid 21st century and the second by the end of 21st century. So what you see here is you have more significant increase in winter flow and for the reduction in summer flow. But also there's a lot of spatial variability. This is based on like over 200 sub-basins within the Willamette River. So more increase in winter runoff in the high cascades, the high elevations, but also more decline in summer flow in these western cascade regions. But in high cascade, you don't see a lot of reductions. And why? Because if you look at those 2 different figures, the geology is so different. So the Lookout Creek, which is located in Western Cascade, they have a very shallow groundwater system developed. As a result, the water can move very fast. But in the High Cascade, you have a very deep groundwater system developed. So the water is still flowing out. This is taken the same day in September a couple of years ago. You can see the dramatic differences between those 2 creeks. And also we projected what's going to happen in the Willamette River Basin. So based on some potential shifts in hydrograph by month. And this is just aggregated into much larger geographical area, but still you can see there are some shifts in the system by the end of 21st century. And also, we look at change in snow water equivalent. SWE stands for snow water equivalent, how much water is in a given depth of snow, and over the precipitation, the ratio. So if less snow is available, you expect the ratio will decline. So by looking at changes in the ratio by the end of 21st century, the reference period, the current period, and by mid-21st century and by the end of 21st century, under two different emission scenarios. The A1B is the medium-high emission scenarios, and B1 is low. So you can see by the end of 21st century, the majority of those high Western Cascade basins, the snow is gone. But also we look at some potential frequency of extreme droughts, so over 3 months drought, like a 3 months persistent drought, and compare that, the frequency of drought in the reference period. So again, in the most Willamette Valley regions, you expect a higher frequency of extreme droughts. So what are potential solutions to solve these problems then? So if we have less water available in the summer, but you may need more water, one way you can do is change the dam operation system. We can probably store water until the late period and then release water later. That's one way of doing that. But we can also look at much in the small geographical area. For example, if you live in urban areas, the urban residents also can do something. So this is based on the water consumption data in collaboration with the City of Hillsborough and the Portland Water Bureau, looking at the temperature sensitivity of water consumption at each census block group level. So you can see as temperature rises, people consume more water, and this is just showing if over 100 degrees Fahrenheit, how much water is needed. And we analyze that by each census block group and then compare that with the land density. So not surprisingly, the lower the density, so the houses, you have bigger lots and bigger gardens, they tend to use more water and they tend to respond more sensitive to changes in temperature than census block groups that have a small lot size and with higher density. So in other words, the land use planning can potentially work as an adaptation strategy in this case. So about water quality here. So this is called the United States Environmental Protection Agency created those maps showing which segments of those streams violate a certain standard. So this is that's called the EPA 303D list. So and notice that if you look at by state, the state of Washington doesn't have a lot of these red areas. Doesn't necessarily mean that the condition is better than the rest of the two states. It's the way how they actually organize, how they monitor the system. So that's another political, how the political and social dimensions can also play in terms of representing some environmental standards here. And this is basically going back to the answer. So in Idaho and Oregon, Washington, the first impairment is temperature. Water temperature is number one, and followed by sediment and nutrients. And this is how many lengths of the streams violate those standards. And Washington State doesn't seem to have a lot of miles, but as I explained, it's the way how they organize the data. Are there any potential solutions to help solve this thermal pollution? So this is showing the Tualatin River Basin in western metro area. And by the way, does anyone know what Tualatin mean? It's a native Indian word meaning lazy. Anyone living in the Tualatin River Basin? It's just living very slowly, right? If you are in the middle of the basin, it looks like it's not going anywhere. It just stops. It got stuck. So anyway, it's a lazy river. So what that means is since the river is not flowing fast, it sits there for a while and observes solar radiation and can heat up quickly. So there's a lot of water thermal pollution problems. So what Clean Water Services, the managing agency in the Tualatin River and Washington County, and they have done some stream restoration by planting trees along those riparian areas since 2004. So this is just showing where those stream enhancement projects occurred. So mainly the upper portion of those streams and some tributary streams. So we need to understand if you want to try to improve this thermal pollution, we have to understand what are main driving forces of the stream temperature. So the solar radiation is the main input of the system. So air temperature, if air temperature is rising, streams also observe solar radiation, and then stream temperature will increase as well. But also there is some human influences, like a wastewater is entering into those streams, the stream temperature will go up. But if you plant those trees, and trees provide shading, and as a result, temperature may be cooled down as well. But there's also internal process like a conduction and hydraulic change. The water actually comes out from the stream bed and regulate the stream temperature. So just fundamentally, we have two different factors affecting stream temperature. One is air temperature. You can consider the air temperature may be a proxy for explaining the variability in stream temperature. But the other factor is stream flow. If you augment flow, the more flow in a stream, so the more higher volume of water. So the higher volume of water, it takes more time for water to absorb solar radiation. So stream temperature will go down. So what one of my former students and I did is simulate the potential changes in water temperature under some climate change scenarios. So we assume that there is an increase in air temperature and reduction in summer flow. It's about 5% decline in summer flow in combination with 1.5 degree increase in air temperature. So, and this is showing from the upstream to downstream. So segment 0 showing the upper end of this lower section of the river, and 154, which corresponds to this segment. So it's showing the upstream and downstream, looking at the spatial variations as well as temporal variations, starting from May 15 to October 15. Just make sure that how you understand this diagram. And then each colors represent different temperature. So not surprisingly, toward the end of the summer, in the lower section of the river, you have a higher temperature than the upper part and the earlier or later part of the period. But under those two climate change scenarios, this is like a 1.5 degree increase in temperature and 5% reduction in flow. And this represents 10% reduction in flow in combination with 3 degrees Celsius of warming. So what's the trend here? Those orange arrows expanded over space and time under those climate change scenarios. So expand, so like early part of the year, you get early warming and also upper stretch of the river. So it's a thermal expansion toward upstream, but also expand over time. So can you do anything? If climate is changing, is there any way that we can potentially mitigate or adapt to those changing environment? Anyone recognize where this place is? Here's my kid and his friend. It's a Rock Creek Park on 185th Avenue. Before you go to Rock Creek PCC, there is a Bethany Creek area you can actually fishing, but you can see there are no actually trees along those riparian areas. So what if we plant trees along those areas, can we reduce water temperature as a result? So this is showing some simulations. So we assume that some of those tributaries got riparian planting, and then as a result, the temperature lowered by 2 degrees Celsius. And look at the impacts on the main stem temperature. So you can see immediate section junctions, you see some improvements. But in general, the rest of other parts of the main stem, the conditions didn't improve much. And this is showing, again, it's a complex problem, but this is showing the base case. And this is the climate change, the low climate change, and the high climate change, and the medium land riparian planting. So you only look at 2 degrees Celsius cooling from 6 tributaries, and the last 3 graphs shows the 2 degrees Celsius of cooling from all 10 tributaries. So just looking at this base case, with no climate change, you can see this orange area shrink over space and time, so illustrating that the conditions got improved to some extent. And particularly under those most warming scenarios with flow reduction, you get more significant improvement, at least those reddish areas shrink both over space and time, so illustrating that those riparian planting have some positive impacts in terms of improving thermal pollution. But also we can consider some auxiliary ecosystem benefits of riparian shading. So by planting those trees, you can actually stabilize a stream bank, minimizing erosion. And also by planting those trees, it creates some place for habitats, both aquatic and terrestrial species. But also it could buffer some storm runoff because of trees, and trees can absorb storm runoff. Let's just skip it. And there is also other solution that we might want to consider, more like a structural solution. So this is a current situation. So we have a dam, and we actually release water at the bottom of the dam. It's too cold, so adult salmon cannot migrate to spawning grounds as a result, because there is a stratification of temperature. It's very warm at the top, but it's very cold at the bottom. So how can you solve that situation? Is there any way that we can solve it? And this is another condition. If reservoir level down, and during the fall and early winter, the water temperature is too warm, preventing salmon eggs hatchery. So one way you can do is combine warm and cold water together. So there is a surface sphere. So if you mix the top portion of the water and the bottom portion of the water, mix it and release it, and correct the temperature. So this actually happened in Detroit Dam in North Santiam River, and people are trying to look at the impacts of those new temperature control on stream temperature. And this is another way to make a new intake tower. You can actually mix water and all together, and then release the mixed water at the bottom of the dam. So they are thinking about constructing this new intake tower in Detroit Dam by the end of 2018. So this is one way of investing some money to improve thermal conditions here. But also the sediment is another concern, particularly in some eastern counties in Washington and Oregon. So here's one example how they did improve some soil erosion in Paros River Basin. So the Paros River Basin is located in eastern Washington, as bordering the state of Idaho, and you can see a lot of ag land within the basin. So agriculture is the main industry in this basin. And people found that since the 1960s, they introduced a lot of these best management practices, and they did find that erosion level dropped by 10%. And this is showing how much soil erosion versus how much sediment is. So there's a close relation between how much sediment in the river is associated, how much erode material from upland. So what they did is, one way is you can use the no-till seeding. So instead of using those big, heavy tractors, you allow no-till seeding, and you can also control erosion. And there are some other ancillary ecosystem benefits. By doing no-till seeding, now you can have more organic carbon. This is showing different soil layers. All stand for organic carbon. You have more humus, like organic materials here. And those organic carbon can sequester carbons, can reduce greenhouse gas emission. Also, by not using these heavy tractors, and you use less oils and greenhouse gas and less energy. But also because those organic matters and like earthworms have holes that can capture moisture more efficiently, you may be able to reduce the amount of water needed for irrigation. And also, those earthworms and other creatures can maintain biodiversity. So those are some ancillary ecosystem service benefits that we may expect. So this is on results. This is taken from the USGS report showing substantial decline in sediment load in the basin. So compared to early 1960s versus 1990s. And I downloaded some of the USGS data and to look at whether there's the relationship between discharge and sediment concentration has changed over time, and for 3 different periods, 1960s and 1990s and 2000. So what you see here is there's a general decline in suspended sediment concentration, even though with the same discharge amount. For example, here 1,000 cubic feet per second, you have about less than 100 milligram per liters of sediment concentration in the 2000, but in early 1960, you get close to 10,000 milligram per liters. So that clearly illustrates there's an improvement in the system by introducing those BMPs. So we could make changes. But how about the nutrients? This is showing a study by Dan Wise at the USGS at Portland office. So their team developed some spatially detailed regression model showing those nitrogen yields. And you can see the Willamette Basin and there's some coastal basin, you have higher yields than the rest of other more inland. But also you need to understand what are the main sources of those nitrogen. So you can consider those 4 different sources. So you can argue the agriculture by the fertilizer is the main source of nutrient, nitrogen in here. So all these lowland areas, the agriculture is the main source of total nitrogen load. But if you look at some forest lands, the atmospheric deposition is the main source of total nitrogen. And in urban areas like in Seattle and Portland, the urban people fertilize their lawns, and during rain events, those when people apply excessive fertilizer, they release and entering into the water body. So that's why those urban areas are showing the main source of the nitrogen here. But also there are a lot of some wastewater treatment plants along these streams. So in other words, we have to understand those different sources, and they vary over space. So in other words, we need to understand especially explicitly. Otherwise, there is no one solution fits everything. So the USGS scientists have created a wonderful model try to engage those stakeholders in the region. I'm going to share this with you and hope that works. Oh, not sure why it's not working. So what it shows is essentially you can actually click here, and this is showing the Columbia River Basin. And by each area, you can simulate. I think I actually opened up in here. Maybe it might work in here. So if you click here, and you can choose like a nitrogen, and it will show some maps and which area you want to go into. And if you live in that area, you can actually see the condition of your place and how you can manage the system in a more interactive way. So in this sense, this geospatial technology will become a powerful potential decision-making tool by engaging those stakeholders, and then they can also interact with any system changes. And the other thing we also did is looking at some complex institutional arrangement. And also there is different scales of those arrangements from the state level, the federal and international. And we have also Columbia River Treaty, which we need to negotiate sometime soon. But at the state level, for example, in the state of Oregon and Washington and Idaho, they have very different state regulations. So we have to understand those different governance systems, try to solve the complex water problems. So with that, I would like to conclude some preliminary results. We all know that land cover, which is reflected by population growth, is very closely associated with water resource vulnerability. And we also notice that climate change will bring additional vulnerability in terms of water quantity and water quality, particularly in urban areas. They may get more significant impacts by climate change. But we also know that there are some solutions we might do. So like a land management and regulation, like a restoration of floodplains or planting riparian areas that may serve as climate adaptive strategies. But also notice that the spatial, we need to understand those complex spatial patterns. So any impact assessment need to be done in a spatial explicit way. And also we need to invite stakeholders at the beginning of the project. And in this way, we can truly achieve the integrated water resource management. And finally, we also need to understand this multi-level water governance. And so with that, I'd like to thank everyone attending late Wednesday evening. And I'd like to take any questions you may have. Thanks.
Questions? Yes, please. Please, you have to go to the mic. We are live streaming it and we are video recording, so please.
When you were looking at temperature changes and relating that to water usage changes, did you notice differences within the census blocks if institutions or commercial buildings used more compared to residents because they don't necessarily pay out of their personal pockets?
Yes, that's a very good question. But at the county level, we don't have that detailed level of data. But at the city level, like the Portland Water Bureau, the water provider, they can provide the detailed water consumption data by customers, and we can do analysis at that small spatial scale.
A question from the online audience. It says, can you expand on aquifer water recovery? Is this really a viable solution for areas with high water consumption? I wonder about monetary costs and whether it outweighs the amount stored.
Yes, I'm not an expert in aquifer storage. So there's maybe groundwater hydrologists working on that, a project at OSU. But there's probably one technical solution people are considering. And I know that the Umatilla County is considering that option, and that they say that it's a viable economic solution. So I don't know the details about the cost of that.
There's another one, if you don't mind. What are financing options available to government entities for infrastructure projects like dam water mixing systems and tree planting along rivers to control water temperature?
I know that in the Tualatin River, the Clean Water Services has done a feasibility study. So instead of creating a new wastewater treatment plant in the downstream, they did restore upstream lands, and they found that that's much more cost effective. But I don't have the number on top of my head. But if you're interested in reading that work, Bobby Cochran at Clean Water Services, he and his colleagues have published a paper in the Journal of the American Water Resources Association looking at that particular case study. So they do have some numbers in that article.
Thank you for a very interesting talk. What would you characterize as presently the most effective forum by which cooperative discussion across all these basins and states and entities can presently be conducted, and what would your recommendations be for a more effective framework for collaboration?
It's a very good question, and I think there is a movement among the different government agencies, including USGS and U.S. Army Corps of Engineers, and they are discussing ways how we understand the whole system, and for example, like how do you improve the water quality conditions. There was a workshop in a couple of months ago, actually back in June, and they invited the people from EPA and USGS and U.S. Army Corps of Engineers and some university researchers, and they did identify some problematic areas in terms of like hotspots. Where are the sources of those water pollutions, and how each different agencies can work together. I think it's probably more like a higher level at the federal agencies may facilitate that discussion, because I know that the state agencies may tend to work their own jurisdictional boundaries. So maybe may need a kind of inter-jurisdictional committee overarching those state work. Yeah. And also the university and those research agencies like USGS can work more together, and also the stakeholders. So maybe we need some kind of organization that can overarching that multi-scale governance, which is lacking because the system may be fragmented at this stage now. But I'm not also the governance person. There are a lot of other folks working on that area on campus, yeah. Like Jennifer Allen, who was here before, and Connie Ozawa at Urban Studies and Vivek Chandras. Those are the folks who are working on water governance and water management. Yeah.
I want to say also thanks for the presentation. It was really great. My question is, one of my professors said that the water, we're trying to conserve water and trying to do all these good things, but he said that water doesn't disappear. The water is always in the system. I just wanted to get your opinion on that. And so if water doesn't disappear, where does that water go? I mean, is it stored in ice and just sits there? Or does it melt away, and where does it go? If it doesn't disappear, where does it go? Or just if you can clarify that.
Yes, as you know that the Earth is a closed system, so the water is just a closed system. We have a finite amount of water. But the thing is, it's a spatial and temporal distribution of water. That's how it may change in the future under like a climate change and urban development, and how we allocate water in a more equitable way, both over space and time. That's how the water resource managers are concerned about these days. But you're right, so the water is a fixed amount, but it's recycled, the rate of cycle. For example, if the climate is changing, the warmer the atmosphere may hold more water vapor. So it accelerates the water cycle, so you may get more intense rainfall as a result. So you can see you have more actually drought as well as more intense rainfall. But the annual precipitation doesn't change at all. But the intensity of those extreme events may shift. All right, thank you.
Okay. Thank you very much. And we can continue the discussion over some refreshments. So please feel free. Thank you.